Okay, so today we'll do a revision on revision problems on chapter 3. We discussed in chapter 3 several strategies to enhance the performance of thermal power plants, and we discussed one of the technique is cogeneration. We'll see together that cogeneration will allow us to enhance a lot the efficiency of our system, as this example will show. So we will consider a cogeneration plant that is shown in the following figure. Now here, if you want information will be important for us in order to draw the TS diagram from our given. Okay, so we know first that the steam entered turbine at 7 megapascal and 500 degrees. So this is the conditions at turbine inlet. And in general, turbine inlet is superheated vapor. So all we have to do is to go to the tables, and from tables, we can get the enthalpy and the entropy at this state. Now, some steam is extracted from the turbine at 500 kilopascal for process heating. When they tell you that we are doing process heating, this means that the power plant is not only used for electricity production. So we have seen that whenever we say cogeneration, this means that the power plant is designed to produce electricity and to produce heat. And where can we extract the heat? It is through the process heating. Okay, so we use a process heater equipment that will take the energy from our fluid and give it to a liquid, for example, like water. It can be, for example, a heat exchanger that will take a heat from the fluid circulating in our power plant and will give it to any other fluid. It can be for water heating application, for example, etc. So we can put or a heat exchanger or a process heater in order to extract energy in form of heat from the fluid. Now the remaining steam continues to expand to 5 kilopascal. So we can understand from this given that we have 3 levels of pressure. You have the high level of pressure at boiler. You have the low pressure for your condenser, and you have an intermediate pressure where you extract steam that will go to the process heat. And we'll discuss this now in the graph. After this, steam is then condensed at constant pressure and pumped to the boiler pressure of 7 megapascal. At time of high demand, so in this problem, we'll see that we'll put equipment in a way to control the percentage of process heat and the percentage of electricity. Depending on the load, we'll decide what is the fraction that should pass by the turbine, what is the fraction that should go to the process heater. So at times of high demand for process heat, some steam leaving the boiler will be throttled to 500 kilopascal and is routed to the process heater. The extraction fractions will be adjusted so that steam leaves the process heater at saturated liquid of 500 kilopascal. So we know that at the exit of the process heater, we have a saturated liquid state. In general, if they don't mention anything for condenser and process heater, the exit will be saturated liquid. The mass flow rate of steam through the boiler is given. So this is the total mass flow rate, m dot total, okay? And this total mass flow rate can be divided into parts depending on what is the percentage of electricity and what is the percentage of process heat that we want to produce. So this is the total mass flow rate circulating in the boiler. Disregarding any pressure drops and heat losses in the piping and assuming the turbine and pump to be isentropic, so this means that whenever we say isentropic process, so S is constant. We want to determine first what is the maximum rate of process heat that can be supplied, what is the power produced and the utilization factor when no process heat is supplied, and finally, what is the rate of process heat supply if 10% of the steam is extracted before it enters the turbine, and 70% of the steam is extracted from the turbine at 500 kilopascal to cause process heating. So now let us see the figure and do the analysis of the figure to be able to answer the questions. In the exam, we give you this figure, and you should be able to draw the TS diagram, okay? So here we have the scheme showing the different equipment, the turbine, the boiler. We have two pumps here because we have three pressures. So whenever you have three pressures, you will need two pumps, okay? And we have the process heater and a mixing chamber here. Let us discuss what will happen in each of these components, okay? So first we say point one is the exit of the boiler and the inlet of the turbine. And this point the states are given, the properties of this point are given. We know that the pressure is 7 megapascal and the temperature is 500 degrees. And if we go to the tables, of course, this will be a superheated state. So going to the table and searching for a pressure of 7 megapascal and a temperature of 500 degrees, we can find the enthalpy at point 1 and the entropy as 1. Okay? And then we'll be able to locate this point on the graph. And since this fluid, okay, is the total mass flow rate, so we can put here that the fraction of mass flow rate is 1. So first we have 100% of the flow going from 1 to 2, okay? Now what will happen? We have the possibility of extracting a certain proportion to go through the expansion valve, okay? So I can say that what will go from 2 to 4 can be a certain percentage or fraction X, okay? So, and what will happen in the expansion valve? An expansion valve is a device that will allow you to expand your flow without losing any work or heat, okay? And you know that for any system that you consider, what is the equation that you write? You write Q dot minus W dot. Since we have here one inlet, one outlet, it's equal to M dot times so we have here at inlet we have H2, at outlet we have H4. And since in the expansion valve no heat or no work rates, this will be equal to 0. And we deduce that in our expansion valve, the enthalpy will remain the same. So H1, which is equal to H2, is equal to H4. Okay, then all I have to do is to consider this line, okay, of constant enthalpy. How we draw a line of constant enthalpy in TS diagram? It's a curve for which S is increasing, because you know in any process, okay, we have that what will happen here, we have an expansion, the temperature will be reduced and the entropy will be increased, okay? So this is our figure representing the variation in expansion valve from 1 to 4. And because they told us that it will expand to 500 kilopascal, then we'll stop at the intermediate pressure line. So we have here 3 pressure lines. If you want to illustrate them, you have the high pressure line here. So this is the pressure line of 7 megapascal. Okay, we have the intermediate pressure at which we have the exit from the expansion valve is 500 kilopascal. And for the process heater, The process heater is characterized by constant pressure. Yani all inlets, it's like if you want a mixing chamber. All inlets and outlets should be at the same pressure. So that's why 0.4 should be on the pressure line of 100 kilopascal. Okay. Now, as we said, so the flow that will reach this level will be divided into a proportion going to the expansion valve and a remaining part that will circulate in the turbine in a first stage. So it will be 1 minus x. So between points 3 and 5, okay, you have 1 minus x that is circulating. So you have expansion, and you know that expansion in a turbine is isentropic. This is a two-stage turbine. This means that first I have a first stage of expansion from pressure of 7 megapascal to pressure of 500 kilopascal. And if you check from tables, okay, you know that 0.5 is characterized by two properties. So since isentropic process, S1 is equal to S5. And you know the pressure at this level is 500 kilopascal. Okay, so then you can go to your table and check that at this pressure Sg is larger than S5. This means that you have a mixture here, and you can find the quality of this point. So you can say I can get X5 by doing S5 minus SF over Sg minus SF. Okay, and once you do this, once you find the quality, you can calculate the enthalpy at 0.5 by doing X5 is equal to H5 minus HF over Hg minus HF. Okay, so now you are able to determine state 5. And as we discussed, what is the mass flow rate going from 1 to 5? It is equal to 1 minus x. So the proportion of the total flow rate is m dot times 1. If you want to find the mass flow rate circulating here, you multiply the percentage or the fraction 1 minus x by m dot total. Okay, now what will happen then at this level at 0.5? You have two possibilities to continue, or you can extract a certain part to go through the process heater, or you can expand into the second stage turbine. Okay, so this is why here we say that a fraction y will be extracted from the first stage turbine to the process heater. So now what will continue here, okay, is the fraction y in the process heater, while the remaining part that will expand to the lowest pressure, which is 5 kilopascal, is a proportion 1 minus x minus y. Okay, and of course it's an isentropic process because they told us to assume ideal processes. So S5 equal to S6 equal to S1, and we can find then H at 0.6. Okay, now 0.8 is the exit of the condenser. It's saturated liquid as usual. Now what will happen is that the two parts that are extracted first at expansion valve and at first stage turbine will mix in the process heater. They will mix together, okay, and they will exit at state 7. And the process heater is a very important part because what will happen is that in this process heater, we'll be able to deliver heat, okay? So we can deliver heat to the surrounding. and we call it Q dot process. Okay, and in order to determine how much heat we can give to the surrounding or to a fluid that is needed to be heated, and for example, if you consider water for residential application, you need hot water for residential application. So you can use this process heater to heat the water, and you can then use this water, this hot water for any application. Okay, shower or hot water needs, etc. So in order to determine how much heat we can extract at the process heater, we need to do the energy balance for the heater. So if I take the heater as a system, all I have to say is I apply as usual the energy balance. And since in the process heater, I can expect that Q dot will be negative because it's out, okay? So you can say minus Q dot process, okay? Because it's out, okay? And no W dot, so no work here. If you put minus W dot, it's zero because you have, in this case, it's a rigid system, so no mechanical work and no production of work here, so no W dot through the process heater, okay? Equals to sum of M dot NHN minus sum of M dot out H out, okay? And then all you have to do is to determine where are my inlets and where are my outlets. So you can say that minus Q dot P is equal. So here, what do I have as inlets? I have points 4 and 5, okay? So I have that, just here, sorry, it's out minus in, okay? Because when you write your relation, if you have here, you put the outlet minus the inlet, because when you give energy to your system, what will happen? When you give energy to your system, the energy at the outlet will increase, okay? And when you take energy from your system, you will lose energy. So we say that the balance Q dot minus W dot with the surrounding, the exchange with the surrounding, is equal to sum M dot out H out. So just if you remove the minus, if you put plus here, if you just put plus, you will get it as it was, okay? So if you put plus Q dot process, which is the amount of heat release, you can keep then sum of M dot NHN, okay, minus sum of M dot out H out, okay? So let us see what are the inlets and outlets that we have. So we can say that in overall, the extracted heat, Q dot process, is equal to, what is the mass flow rate going through for? We said we should consider the percentage fraction X. So it's X times M dot H4 plus the fraction that will go through the process heater is Y. So it's a plus Y M dot H5 And now what will go through 7, so the two flow will mix together, okay? And you have one exit. So that's why at this exit, the proportion will be x plus y. So you have minus x plus y m dot times h7, okay? So in this way, you can deduce what is the amount of process heat. And in this example, they told you, if we go back to the given, they told you that 10% is extracted before it enters the turbines. So this is X. So this is the fraction extracted to the expansion valve. So you replace X by 0.1. And 70, and they said then 70% of the steam is extracted for process heating from the turbine. So Y is, the fraction is 0.7. Y, X plus Y is 0.8. Okay. And since you have the total mass flow rate, which is 15 kilogram per second, and you determined all states H4, H5, H7 from the analysis of the TS diagram, then all you have to do is to replace and get in this condition, in part C, what will be the process heat, the total process heat, okay? Now, they also asked here to determine several things. The maximum process heat that can be supplied, and also the power that can be produced if no process heat is supplied, okay? What is the difference between these, all of these cases? The main difference here is what are the fractions x and y that we will extract. So let us discuss together the graph here, okay? We said that we can produce electricity through which cycle? Through the convention cycle. And if I consider first boiler, turbine, condenser, and pump, okay? If I just go through this path, this is my conventional power plant system. This is the conventional Rankine system. And then I can just produce electricity. To do this, I don't want to extract any fraction through the expansion valve. And I don't want to extract any fraction to the process heater. So I put then x equals 0 and y equals 0. Okay. And in this case, my utilization factor is similar to the thermal efficiency. Okay. Because when we say utilization factor is, if you want, energy, it's useful energy, if you want. So whenever they tell you utilization factor, UF, so utilization factor is the useful energy that I produce. It can be of different type. It can be electrical, it can be heat, okay? And just I need this energy and I can use it. So it's useful energy over input, okay? Over the input energy. So in this problem, in the first question, if I just want to produce electricity, for example, so what should I do to just produce electricity? I don't need any process heat. I just have to shut down, if you want. And I don't use these parts. I don't extract any fraction to the expansion valve, and I don't extract any fraction to the process heater. So the mass flow rate will completely circulate into my conventional Rankine system. And then the utilization factor, which will be equivalent to the thermal efficiency, it's W dot net over Q dot N. Over Q dot N. Okay, so in this case, what is W dot net? Let us look at our figure. We have production of work through my turbine. So here I have W dot turbine. And since I have no extraction, no need to divide into two stages. So I say I expand from 0.3 to 0.6, the total mass flow rate. Okay, because we said that this is 1 minus x and this is 1 minus x minus y, but now x and y are 0, so I will go directly from 1 to 6 with the total mass flow rate. Okay, because I have 0x and 0y. And then as usual, all I have to do to get the efficiency, I do m dot. For the turbine, I have H1 minus H6, or H1 is equivalent to H3. So it's H3 minus H6 over Q dot N, which is M dot, so over M dot times, in the boiler, I have between points 11 and 1. So I just do over M dot H. And point 11 here will be exactly the same as point 9. Why? Because what is point 11 here? Point 11 is the exit of the mixing chamber. The mixing chamber, which is mixing two fluids, one at state 9 and one at state 10. But here, since I'm not mixing anything, I have one flow. So 0.9 and 11 will be the same, and 11 will be here. Okay, that's why I will just take H of 0.9. So it's M dot H1 minus H9. So this is the conventional way that I usually do. It's the Rankine cycle. And in this case, I only produce work. I'm not producing any process heat. Okay. Now, in case, so when I do this in peak hours of electricity load. So I need a lot of, I have high demand for electricity, much more important than process heat application. So I just have to function my system as Rankine cycle. Now, let us say now that I don't want to produce any electrical power. I just want to have process heat. If I want to do this, I should not pass through the turbine. So in this case, I will do the following. When I exit my boiler, I fully expand my fluid in the expansion valve, and then it will move through this pass. It will move through this pass, and this will be my cycle. Okay? And in this case, if I have an ideal system, actually, I will use, if you want, a big amount of energy. Why? Because if you want to calculate the useful energy here, what is the useful energy? It's the energy that I am able to extract at the process heater. And if I consider the energy balance of my cycle, what can I write? I can write that Q dot into my boiler minus Q dot process that I am extracting. And you know that for the pump, okay, for my pump, I should supply work to function my pump. So I can say then minus, so I need to supply work here, okay? That's why I can consider that I need this work should be supplied from the energy that I have. That's why I consider that I should put minus W dot pump to equals to 0. Okay, so what will be then the amount of process? This is the maximum possible process heat that I can extract. Why we say it's the maximum possible? Because you know, we have always losses, okay? And how can I tell you, if I tell you, for example, the process heater has an efficiency of 90%, then you will say that the extracted heat is 90% times the maximum possible extracted heat, okay? هلا we'll do it in the calculation. So here I do Q dot process maximum is equal to Q dot N minus W dot pump 2, okay? And then the maximum process heat that I can extract will be equal to, so we replace, as usual, we replace m dot n. So here, m dot n is between which points? 11 and 1. And here, what is point 11? It's equivalent to point 10. Why? Because as you can see, we didn't mix 10 and 9. So the mixing chamber will not do any role here because the fluid will enter, okay, and will exit at the same state because it's not mixed with any fluid. So now point 11 will be here if you want. It will be equivalent to point 10, okay? And that's why when I do my calculation, I will replace Q dot N by M dot H1 minus H10. And for my pump, okay, so minus m dot times, and here the mass flow rate is the same because we don't have any extraction. It's the same mass flow rate circulating in all parts of my system. So minus m dot times, for my pump, okay, we have to do H out minus Hn, so H10 minus H7. Okay. And then I can calculate the maximum process heat that can be delivered. And what will be then the utilization factor? Here, the utilization factor of process heat, the maximum utilization factor of process heat is equal to Q dot max, Q dot P max over Q dot N. Sometimes if I give you a percentage, and if I tell you the process heater is 80% efficient, all you have to do is to multiply. So when I give you the efficiency, so you cannot say that this is the maximum utilization factor. You say that I am just able to use 80%, for example, of this maximum process heat. So since I'm using only 80%, so the useful amount is 0.8 times Q dot max, and I divide by Q dot N. So in this way, I can find the value of my utilization factor if I have 100% process heat used, okay? And in general, we use cogeneration, and at the same time, we produce electricity and process heat. And to do this, all we have to do is to play with the fractions. So what is the fraction? We can take a fraction here, a fraction here, depending on the energy that we need to extract. So it's very simple. We know that we want to have here a saturated liquid, okay? And so we know states 4, 5, and 7. So if we impose a certain process heat to be delivered, we can select X and Y in a way to produce this process heat, okay? And then what will happen is that different mass flow rate will circulate in the cycle. And as we said, we should annotate them to be able to answer what is the utilization factor, because now it will become more complex to assess the utilization factor, because it will consist of W dot net plus Q dot process. of course, the useful one, يعني, if we have a percentage, just you multiply Q dot max by the percentage given over Q dot N. Okay? And now just we have to evaluate what is W dot net, what is Q dot process, and what is Q dot N. Let us start by W dot net. Okay? So here you have two stages of expansion. So you have W turbine 1, W dot turbine 1, and you have W dot turbine 2. And of course, you know how to calculate them, okay? So just you should say, what is the fraction circulating in the first stage? It's 1 minus x. So I do 1 minus x times m dot times h at the inlet of the turbine, which is at 0.3, minus h at exit of stage 1, which is 5. So h3 minus h5. Second step, I consider the second stage. In the second stage, what is the mass flow rate circulating? It's 1 minus x minus y times m dot, and I multiply by h. So now the expansion is from 5 to 6. So h5 minus h6. Now, concerning our pumps, okay, in pump 1, what is the mass flow rate? It's the proportion is 1 minus x minus y. It is the one that is going through the second stage turbine. So 1 minus x minus y times m dot. So for my pump, as usual, the work that should be delivered to my pump, I put h out, which is h9 minus h8. And for my second pump here, what is the mass flow rate circulating? We already discussed it. It's x plus y. So m dot times x plus y times h10 minus h7. Okay. So then I can calculate W dot net, because W dot net is W dot turbine 1 plus W dot turbine 2 minus W dot pump 1 minus W dot pump 2. And then to calculate Q dot process, it's exactly, we already did it together. Okay, you just have to know what are x and y. You calculate Q dot process as we did. And just now for our boiler, it's m dot h1 minus h11. Just to get h11,